Hey everybody, how's it going? Waiting for more people to come in. Just wait till 5:45, guys. We'll get started. All right, it's time to get started now. So I've got the roll, and obviously not nearly a decent sized fraction of the class, but time has started, so let's get cracking. I'm sorry, I was supposed to post a video. I've had now 4 incidents that have prevented me from actually making the video. I actually made mistakes, and it takes way more time to edit them than it does to just redo them. So I was redoing them, but I keep screwing up. So that didn't go well, and I had a series of other problems. But what I thought I'd do, and you guys are not required to stay the whole time, but I am going to go ahead and do a lecture in real time on chapter 29, sort of the most critical parts of chapter 29, and I'm probably going to go into chapter 30 as well, depending on how much time it takes. So you guys can sit back and watch, or now that I've got you on the roll, you're of course free to go after anytime you feel comfortable. But the main thing is I wanted you guys to make sure y'all had some intro to chapter 29, because I did make the last test, which is not the final exam, by the way. We still have the final exam, but I did make the last test available, and it does cover chapter 29. So I am still leaning towards the final exam, maybe just being on those last chapter or two. So I wouldn't worry too much about trying to do past stuff and try to recap on that. I just don't think it's very conducive. It's the best way to learn, so it would obviously be great if you guys went back and took your old tests and figured out how to do the things you missed, especially if you're going into EE, electrical engineering, or you're doing something directly related to this physics related stuff, electricity, magnetism, or any of that kind of stuff. Other than that, it's really just a matter of you becoming mature enough to apply mathematics at this level to solve physical problems. So I think you get that whether we do a comprehensive final or not. So anyways, let me start off. I'm going to show you this cool little device. This used to be, I don't know if you ever seen those little candy canes that you get around Christmas time, and they're filled up with M&Ms or various other kinds of candy. So I had one of those. Actually, it got mangled on the top of it, but I used this for a neat little demonstration in my class. You can see it's sort of a wire coiled around a spool. In fact, I got lazy and just bought the spool of wire. So you can see the wire name there. I just got lazy and bought the spool of wire rather than have to wrap anything. This is 16 gauge, quarter pound of 16 gauge, 1/4 inch wire, or 1/4 pound of it. And what I decided to do was take the two ends, and of course this stuff, when it's orange looking like this on the edges, that means it's got some kind of laminate. It's normally some kind of polyurethane they put over it that makes it sort of like a housing. So it's not really that good of a conductor. So you actually have to take a little sandpaper and scrape the ends. And that's what I did. I just scraped the ends off. So I had two terminals, and I took it and connected the two terminals. Trying not to have a hard time here trying to figure out where the actual camera is. So you take these two terminals, and I connected them with what used to be an old flash cube cell. So if you remember, well, none of y'all are old enough really to remember this, but basically there used to be flash cubes on top of cameras, and they were a cube, and they had, of course, 4 sides, and each side had a little glass tube with 2 little wires sticking out of it, and inside that glass tube was basically gunpowder and some metals that burn really bright. And each each glass tube had that in it, and each glass tube had 2 wires coming off of it, and they connected down to the bottom of a terminal on the bottom of the cube, and basically it sent electricity up through that cube, and that caused the flash. So what I did is I bought as many of those flash cubes as I could when they started going out of business, and I connect them to this when I do demos. And all I do then is put this on a large tube like this, and I take this, it's called a cow magnet. I've heard stories that they actually let cows swallow these, and the cows poop and it gets any excess metal out of their bowels. I don't know how true that is. I didn't hear it from a farmer, but anyways, someone told me that one time, and I made some sense in it being called a cow battery, but again, I have no idea if that's true. So what you do is you drop this battery through this coil, and when it falls through, it actually generates electricity, and it would cause the flash to go off. So it's kind of cool. I love that demo. It's really nice. I didn't have the parts here with me, so I couldn't actually do it. All I had was that part, but not the actual flash cubes. They're in my office. But that's a good introduction to basically Faraday's law and Lenz's law, which sort of gives you the direction that the current goes. So let me refer you to my dot camera real quick. And again, those of you who just came in, I'm telling everybody that I had, again, some technical difficulties that prevented me from completing the videos. So I decided in real time to cover the important parts of 29 and maybe even chapter 30 now. So if you guys don't have time, y'all are just planning on a quick question and answer session, by all means, let me know you have a question. I'll answer it. When you get all your questions answered, you can split, or you can stay and try to learn this material I'm giving you. So I want to turn it to the dot cam and start on 29. Does anybody have any questions before I start, though?
I had a question about the final,
For it, Gene.
because I signed up for the 6th.
Uh-huh.
Is it just going to be the normal process, just at 5:45?
Yeah.
It's going to be open for me?
Yeah, I didn't. I wasn't able to get any of the software type stuff that I wanted to implement. So it's just going to be a short amount of time for you to solve however many problems I'll put up there. Usually I make enough problems for it to take on the order of at least an hour and a half, but it's supposed to be up to 2.5 hours. But I'll probably make enough for at least an hour and a half and put that up there.
Okay.
They should be multiple choice. If not, it might be one or two problems where you have to type in something, but I'm leaning towards multiple choice just to get it over with quicker.
Okay.
Also, you might have missed it. I'm also leaning towards this last, the final exam being more like a last test. So
Yeah, you said 30 and 31.
yeah, probably 30 and 31, something like that. And I'll try to make it sort of streamlined. I think it's more important at this point for you guys to get a little bit more feel of the stuff that we're doing as opposed to going on beyond and covering quantum and all that good stuff.
Right.
Okay.
Okay, thank you.
Anybody else? You're welcome, Janie. All right, well, let's go ahead and get started. I'm going to show you my document cam and give you an idea. So it turns out that there's all these neat, interesting relationships between electricity and magnetism. And late in the 1800s, people were, or actually in the mid 1800s, people were really trying to figure out what those connections were. And one of the people was a guy by the name of Faraday, and the other one was a guy by the name of Joseph Henry. And Joseph Henry was in America, and he actually completed the work first, but being in America, which is sort of the backwaters, his publication didn't come out in time, so Faraday beat him to it. But both are really brilliant, and they both deserve credit. So we now have Faraday's law, which could have been Henry's law. But you'll learn later we have units of the Henry, and we have the units of the Faraday and stuff like that. So are different terms in which Faraday's used. And that gives them proper homage, if you will. So one way you might try to examine Faraday's law is just imagine a solenoid. You remember learning about solenoids before. So the solenoid is a coil of wire going along one long axis, so it has an axis of symmetry. It's usually fairly thin in diameter and relatively long in length. So you can imagine this as a solenoid, if you will. And I'll take the last coil of wire, and instead of connecting it to a power source, I'm going to take the two ends of the wire and connect them to the terminals of a galvanometer. And the galvanometer, you might recall, is basically a device that any current that comes in then goes around a coil that's wrapped around a piece of iron, for instance. And that piece of iron is able to spin on an axis between two magnets. And then it leaves that coil and goes back around here. So it actually allows for a closed circuit. So if any current's going through here, it's actually going to go around the coil that's wrapped around iron. And then that coil that's wrapped around the iron is in between the north end and the south end of a battery. So it's sort of like you got a north end of a battery, or excuse me, of a magnet, not a battery. And I got a south end of a magnet here. And I basically have a chunk of metal that has a coil of wire wrapped around it. Now it's on an axis so it can spin, but it's also connected with a spring so it can lock it in one particular spot. So normally speaking, that actual spring keeps the needle pointing straight up and straight down. If current goes one particular direction through this coil, it'll cause the needle to move to the right. If it goes the other direction, it'll move to the left. And in fact, it's got a scale on it so that you know a certain amount of current will bring it full scale, half as much will bring it half scale, and the other direction, the same as the half as much will get half scale, and the other direction full scale will be the same as well. So that's the galvanometer. Now, in order for Faraday and Henry to actually study this, they then took a magnet, and they noticed that when the magnet was actually inserted into the coil and left still, nothing happened. When they took it out and laid it you know, any distance away, whether literally the magnet could be right here, the magnet could be right here. When it's just sitting still, nothing happened again. But what they did notice, is they were paying close attention, is when they actually put it in or took it out or moved it closer or moved it farther, every one of those motions caused this needle to wiggle one way or the other. So eventually they figured out Faraday's law, and I'm going to write it here, and I'm going to leave a space in there for a good reason. But it's called Faraday's law, and it's written like this. This E, which is the induced EMF, so it's an induced electromotive force, which you might remember is just a fancy word for voltage. That induced EMF, according to Faraday's law, is equal to the negative of the instantaneous rate of change of the magnetic flux. So I'm going to call the flux phi or phi, depending on how you pronounce that Greek letter. So d phi dt is the instantaneous rate of change of the magnetic flux. And the magnetic flux is defined the exact same way we did the electric flux. It's an integral of, instead of E, it's an integral of B dotted with dA. So what you do is you imagine some coil, let's say a little coil like this. And of course, it maybe you break it up into infinitesimal little dAs. But if, in fact, the magnetic field was uniform all over, then this magnetic field could come out in front and just be B dotted with the integral of dA. And that would just be B dot A. And that would be the A vector. And the A vector is perpendicular to a surface that sort of spans that circular loop, or that loop, if you will. So if you imagine, for instance, this circle right there, then, or let's do this one. If you imagine that circle right there that you see inside the bottom of that cup, okay, then that surface could be the A surface. If you made a vector perpendicular to that and made its magnitude equal to the magnitude of the area, then that would be the A vector. And then if it was completely submerged in a uniform magnetic field, which is what we had already assumed, then the magnetic field would do something like this. You would see that the magnetic field and the dA are tail to tail, so that would be the angle theta, and you just say that phi is equal to B dot A times cosine of the angle between them. So it basically picks off the component of the magnetic field that is parallel to the A vector, or you might say perpendicular to that surface defined by the actual coil of wire, okay? So that's the special case when the B is really uniform and all that good stuff. Obviously, in more complex cases, you might have to break up A into little infinitesimal areas and then evaluate B at each of those little infinitesimal areas and take a dot product, take the integral. But most of the problems we deal with, you don't have to deal with that, okay? So that is what the magnetic flux is. It's the integral of B dot dA. Notice there's no closed circle on it because it doesn't have to be a closed surface. In fact, it's just a flat surface usually. Now, the other thing is, it turns out that if you have one coil of wire, you might make an EMF given by negative d phi dt. But if you instead go around twice, then it's going to be 2 d phi dt. Or if you go around n times, then the equation becomes negative n d phi dt. Okay, so that's a big deal. That tells us, okay, if I want to make 1 volt, or if I set up a setup where I drop a magnet through and I find that it makes me 1 volt, if I want 10 volts, then I should probably wrap that coil around 10 times and then I'll get 10 volts. Does that make sense? Now, here's the weird part. If we put it in words, Faraday's law includes something we call Lenz's law, which tells us about the direction of the induced current. And this is a really big deal. So if we imagine, let's say, the north end of a magnet pointing down, like you see there, okay, then remember how the magnetic field lines are defined. They leave the north end and go to the south. I use the mnemonic, or I use the memory tool that they're like old people. They leave the north and move to Florida. So the magnetic field lines come out of the north and go into the south. Okay, so what actually is going on here in order for us to understand Faraday's law says that the induced EMF is equal to, in magnitude, is equal to negative times the number of coils times the rate of change of flux. But the negative is really not something we use that much. I mean, it has to be there to make the equations do certain things, like when you put Maxwell's equations all together and make a wave equation. If you didn't have that at negative there, it would screw things up. But in practice, we almost always just calculate it without the negative. But the negative is there because it actually teaches us something about the sign, and that's Lenz's law. Lenz's law essentially says the induced EMF is in such a direction as to oppose the change in flux. So it doesn't oppose the flux, it opposes the changing of the flux. So in this case, if you're considering this magnet falling, you know, so at one point the north end of the magnet is way up here, and the magnetic field's almost zero reaching the solenoid. And then once it gets to this point, now it's a pretty strong magnetic field entering the solenoid. So we'd say, oh, well, B dot dA, clearly the B has increased. The A is exactly the same. It's going to be that area right there. So the B has increased. The A stayed about the same. So the flux is actually increasing. So as it falls, meaning it, the magnet, the flux is increasing. So what Faraday's and Lenz's law says is that a current or an EMF will be induced in such a way as to oppose the change of the flux. So it's going to oppose the change of the flux. The changing of the flux is that the flux is increasing. So this is going to try to fight the increasing of the flux by decreasing it. Well, all a coil of wire can do to really obstruct a flux is it can make a current in it that creates a magnetic field. So if you imagine this little top coil, and whatever it does, all the coils will do. But if you imagine this little top coil, and let's imagine for a second the current going around this way and out over here. Okay, so if we look from above, from the perspective of behind the magnet, it would look like the current's going in a clockwise direction. If that was the case, then I could grab the front piece of the wire right there with my right hand, and my thumb would point in the direction of the current going around that way, and you'd see the magnetic field points down through the solenoid. Does everybody get that? If the current's going around this way, the magnetic field as a result of the current in the coil, forget about the magnetic field from the magnet right now, but if the current was going clockwise as seen from above, would you agree that the magnetic field would be going down the solenoid that way? Anybody not see that? All right, I'm going to assume that everybody got that then. So that actually adds to the magnetic field and therefore further increases the flux. So that's not what is going to be induced. In fact, we now know the induced current should go counterclockwise. And going counterclockwise, notice I grab it with my right hand, my fingers up in the middle of the solenoid would point upward. So the magnetic field then are pointing upward, which is the opposite direction the magnetic field is pointing due to the magnet. So that actually tries to increase, or excuse me, tries to decrease the magnetic flux by fighting the magnetic field. So we now have the conclusion that current induced and EMF induced will be counterclockwise as seen from above. So the current induced will be counterclockwise as seen from the case of the magnet, for instance. Now, as that magnet gets closer and closer and closer, of course, the magnetic field continues to get stronger and stronger and stronger, and the current would, in fact, try to keep fighting it. So it's going to maintain a current. Once it gets in there, things get a little dicey, so we'll leave that for you to think about on your own. But that's the key concept that you got to get. The Lenz's law, that's the most tough conceptual topic in this, probably in this whole semester, is how conceptually conceptually, how does a induced current act in which possible direction? So I'm going to give you a couple of examples of stuff like that. Let's imagine, for instance, that a single coil of wire was like this, and then the wire goes off, okay, that way, so we can actually measure it to determine whatever's going on. But now let's imagine I put a south end of a magnet down here. So that means the magnetic field lines are pointing up when they're strongest. So in other words, you ignore all the stuff on the outside. At the end of the day, really the innermost magnetic field lines are the most important ones because they're closer together and therefore they're the strongest. So in this case, I've got this magnet again falling towards this coil, just like we had before, but this time instead of the north pole sticking down, I had the south pole sticking down. So first we got to ask ourselves, is the flux increasing or decreasing? Does anybody have an answer to that? Can anybody tell me whether as this magnet gets closer and closer to this ring, is the flux, the B dot dA, is that increasing or decreasing?
It would be going from 0 to a negative, so technically decreasing.
Gotcha. That's a good thought. But the key point is the magnitude is really increasing, right?
Oh, yes.
Yeah. Okay. So that's and you're onto something very correct here. So the magnitude is definitely increasing. And remember, we're just doing a dot, so we're not really getting any direction out of it because that's a scalar quantity. But what we're going to do is say, okay, well, the flux is increasing, so I want to actually defeat the flux. Well, currently the flux has the magnetic field pointing up in the center. So if I want to defeat or decrease that flux, I want to create a magnetic field pointing downward. And do y'all see that if I grab it this way, my fingers in the middle will be pointing down, which is the opposite direction that the magnetic field lines point. That addresses your fact that they're negative. Okay, so that would actually do what I want. So in this case, we would get one, flux increasing, and then that would, of course, cause a clockwise current as seen from above. Okay, that's the big concept from this chapter that you want to learn is can I figure out which direction a current would be traveling? Another one that's kind of neat, imagine a current carrying wire. Well, let's imagine just a wire with no current. Okay, and it's next to a loop right here. Okay, this is a metal, this is a metal. All of a sudden, I send a current through here. I0 is equal to 0, but I60 or I6 seconds is equal to 30 amps, say, going that way. Okay. What's happening to the flux through this? Is the flux increasing or decreasing as you go from 0 seconds to 6 seconds? At 0 seconds, there's no current. So is there any magnetic field other than just the earth, say, going through this loop of wire? How about Reese? You out there still?
It says the current at 6 seconds equals what?
30 amps. I just made up a number just to show you that the current's going to be going up 6 seconds later when there's no current at 0 seconds.
When the current increases and moves in the upward direction, a magnetic field will go through the loop, like down into the table.
Exactly. So yeah, it goes from no magnetic field because the current being 0 doesn't create a magnetic field to creating a magnetic field pointing into the table here, right? So that is a flux increasing again. You don't have to do any calculations with this. I'm just trying to figure out now which direction would the current around this loop go. So according to Faraday's / Lenz's law, a current will be induced in this circuit this way or this way. in a way to try to oppose the change in flux. So it's going to try to oppose the change in flux. So the flux is increasing. So which direction do we need the magnetic field induced? I will write this right now, B wire. I know it's really small, but it says B wire. Okay. So the magnetic field at this point, due to the wire, is into the paper. Okay. And the flux is increasing. So which direction do we want the magnetic field induced to point?
Probably out of the paper.
Yeah, you want it out of the paper because it's increasing. We want to decrease it. So that means this little guy, excuse me, I should write it with a circle. This little guy with a dot in the center is B induced. So if I wanted the magnetic field at the center of this circle to be pointing out like this does, then which way does the current have to flow around this way or this way, clockwise or counterclockwise? Remember your right hand rule. Yeah, if you grab this with your right hand rule, with your right hand, such that your finger in the middle of the circle is pointing out, do you see that the wires, the current's going up on this side? And it has to go down on this side. Is that clockwise or counterclockwise?
Counterclockwise.
Counterclockwise, yes. So that's the answer to that one. So B induced is counterclockwise. Now, if I turn the wire off all of a sudden, now the magnetic field would still be going down until the current got to zero. But in this case, the flux is decreasing. So which way would the current start to act then? It's going to try to reestablish that magnetic field, right? So now it's going to try to create a magnetic field going the same direction, which means now all of a sudden it's going to go clockwise. So if I switch the wire from 30 amps to 0, while it's ramping down from 30 amps to 0, the current would be produced in here that's going clockwise now. Isn't that wild? So that's the big concepts that we're trying to learn here. I will write this over to the side. When we go from I equals 30 amps to I equals 0 amps, the flux decreases. It means a magnetic field will be induced down into the page, which means a clockwise current. Okay, so that's another example, if you will, of how the actual magnitudes behave. So now, how do we actually do this? How do we use this to actually solve physics problems? Well, it's pretty straightforward. We normally choose very simple constructs and solve it from there. So one of the examples you might be asked to do is calculate the magnetic flux for a ring, okay? In fact, if you look at example in your textbook of 29.2, that's exactly that type of example. You could just say, let's say we're looking from above. I'll try not to use that blue one. That doesn't show up too well on here. So looking from above, we see a loop of wire that looks just like this. And we see a magnetic field, which I will use blue for, going this way. So we imagine a loop of wire immersed in a magnetic field that's uniform. Okay. Looking from the front, I don't know why I went to red there. what I'll see is that loop looking like an oval because it's not lined up perfectly with my eye. So it'll look like an oval, but the magnetic field, of course, will go like this, 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 just the same. Okay? So if I define, since B is going to be uniform, the flux, which is integral of B dot dA, that magnetic field is a constant. So you might as well just call it equal to B dotted with the integral of dA. Okay? And the integral of dA is just going to be A, so it's B dot A vector. Now there's some ambiguity. Should A be this guy, or should A be this guy? We know it's got to be perpendicular to the coil, but at the end of the day, it really doesn't matter too much because the angle in both cases is going to be theta or theta. Okay? So ultimately, this answer is just going to be magnitude of B times the magnitude of A times the cosine of the angle between them. And that's assuming you put the vectors tail to tail. So you see, remember, cosine has a curve that looks like this. Starts at 1, goes to -1, goes back up to 1. At 2 pi, it's -1, of course, at pi, which is 180. It's 0 at pi over 2, which is 90. But it's a maximum right at pi, or right at theta equals 0. So you see the flux is maximum when the A vector is parallel to the magnetic field, or when the coil is perpendicular to the magnetic field, whichever way you want to look at that. So that's when it's a maximum. So we now have a simple way of calculating the flux. You're just going to do like this: B times A times cosine theta. So if I had theta equals 60 degrees, and I had a magnetic field B whose magnitude was, let's say, 0.40 Tesla. That's a pretty strong magnetic field. And let's say we had an area given by a radius equal to, let's say, 0.05 meters, in other words, 5 centimeters. Then the flux would just be equal to 0.40 Tesla times pi times 0.05 meters squared. So that's B times A times the cosine of 60 degrees. Okay. So if I want to put that in my calculator, I'll do 0.4 times pi times 0.05, and rather than waste time looking for the square on this button, I'm going to just type 0.05 twice. Times, and I'm going to say cosine 60, and I get 0.00157. And the actual units is Tesla times square meters, which we've since defined to be the Weber. So at 0.001, using proper sig figs, 16 Webers. So that's sort of a simplest type problem you're going to solve. Another problem that you'll typically solve, let's say we have a uniform magnetic field pointing out of the page. Very big uniform magnetic field pointing out of the page. So it covers a large space. That's what I mean by big. Okay. And let's say its magnitude, by the way, is just plain B. I'm going to leave everything in terms of symbols here. Now let's say we have some bare metal that makes sort of a bracket, and the height or width, if you will, of that bare metal is L. Okay. And now let's say we take a big chunk of metal and lay it across that railing. And again, this is a big chunk of metal. Okay. And we're going to slide that. Now, since it's metal up against metal, it's actually a conductive thing. So this is a type of loop but we're going to say it's perfectly perpendicular to the rail side and it's moving with a velocity v. Okay? So at a time when this distance is x of t, first thing I'd want to do is calculate what is the flux when bar is x of t away. Okay? So the flux, since the magnetic field's uniform, you can see that it's actually perpendicular to the surface area, which would be this flat surface. So the flux, which equals the integral of b dot dA, the dot product is just basically a cosine of 0 degrees, so that's a perfect 1. The b is uniform. The a doesn't change as a function of b, so it's just literally going to be b times height times width. So can anybody guess the area at this point in time of this rectangle? If you can't read that, that's x of t. So can anybody tell me what that area is? How about L times x of t? And x of t just means x is a function of time. Okay, so we now know the flux. Now I'd like to calculate what is the induced EMF. So that might be part B. Well, according to Faraday's law, E induced is equal to negative N. We only have 1 here, so I don't have to worry too much about that. I'm just writing it so you don't forget it. D by dt of the magnetic flux. So as I said, N in this case is just going to be 1, and I'm going to ignore this, ignore the sign, and just try to figure out what the direction is later. So we're going to say the magnitude of the EMF is just equal to d by dt of b times L times x of t. So the b and the L are constants, so they come out in front, and I get b times L times dx over dt. What is dx over dt? Anyone?
Velocity.
Yeah, and notice I wrote the velocity up here is v, so we know that the induced EMF, at least its magnitude, is b times L times v, where v is velocity. Okay, so I'm trying to make that look more like a nu or a lowercase v, so everybody can tell it's actually velocity, not voltage. Now, if this was like super conductive wire and then this hunk of metal was not that conductive, then the resistance of all this stuff right here is probably negligible, which would be a good thing because as this bar moves further and further, this length of wire and this length of wire is increasing, so the resistance would constantly be changing. But if the majority of the resistance really was in trying to allow the current to go across this bar, then let's say this bar has a resistance R, big R. So now I can ask you another question. What is the induced current? So using V equals IR from Ohm's law, we can say, well, E, which is equal to BLV, is actually equal to I times R. So now I can say I induced is equal to BLV over R. So now I have a new result too. So now I know what the actual current induced is. Does that make sense? And the last thing I might ask is ignoring friction on this rod right here. What is the force required to move this rod? Well, we know that the force on a current carrying wire per unit length anyways, or actually I shouldn't say that. The force on a current carrying wire is F is equal to BIL, assuming that the current's actually perpendicular to the magnetic field, which it is. So I can now say, oh, the force will be B times I induced, so that gives me a B times the B I already had, that's B squared. I induced, again, I'm using B already, so it's LV over R, okay? But now I need the length of the actual bar that's carrying the current, and that's just a plain L, so I'll put an L squared there as well. So I can say F is equal to B L squared V over R. So those are sort of the three biggest types of problems that you solve in this chapter with regards to the Faraday law and Lenz's law. Now, let's look at this now and say first, as this rod is moving this way, is the flux increasing or decreasing? So this question is, which direction is I induced? So the rod's moving this way. The magnetic field's not changing, but you see that the area is actually changing, right? So the area is getting, anyone, bigger, smaller? Come on, guys, y'all know this. You're just not answering. All right, the actual flux is getting bigger. So we say flux increasing. So that's going to induce a magnetic field that's going to try to fight the magnetic field. So it's going to induce a magnetic field into the page. See? It's going to induce a magnetic field into the page because I'm trying to fight the increasing flux. Well, in order to do that, the current has to go this direction, because if I grab it with my right hand, my thumb pointing this way, I see that my fingers in the middle go down, which is the fighting direction. So that means the current induced is actually clockwise. So that's another neat result. Now you can try the same problem again with the current, with the magnetic fields pointing out. You can try it again with the magnetic field pointing, with the magnetic field pointing in. Then you can try it with the magnetic field pointing out and the rod actually sliding this way if you wanted. And then you can again try it with the magnetic field pointing down into the board again, but with the rod moving this way. So there's 4 different problems you can get from that. Hopefully one of those might be able to help you get enough experience so you really know what's going on with this. So those are very classical problems. Another classical problem that can be done, and this relates to everyday electricity, is it turns out that magnetic flux, if you say put a solenoid around an iron rod, iron's ferromagnetic. So most of the field lines, the magnetic field lines, when current's going through that, try to stay inside of this. Obviously, some of them will actually leave, but it actually tries real hard to keep all the magnetic field lines inside the iron. So if I tried to make a circuit where I said, okay, let's do a coil of wire, i.e. a solenoid, and then another coil of wire, i.e. another solenoid, and let's connect them by one of those Thanksgiving Day pilgrim belt buckles made out of iron, okay, then your ideal thoughts would be, if there's a current going through here, it's going to establish maybe a magnetic field pointing this way, and that magnetic field might be able to stay all the way until it gets over to here. If that's the case, if this is what we call a ideal transformer, and that's what this device is when you connect 2 coils with different numbers of turns via something like an iron hunk of metal or whatever, then you get basically a transformer. So you'd say if this is the voltage in, or V primary, and there's N coils on this side, then out comes a voltage out called V secondary, and this is NS, the number of coils on this side. If it's an ideal transformer, then the flux in the primary is equal to the flux in the secondary. Well, we know what the flux is. It turns out the flux is actually N times basically phi. So I should really say the induced EMF, if you will, more so than the flux. N times phi is equal to N times phi. So we'll say N primary times phi primary is equal to N secondary times phi secondary. Ultimately, take the derivative of all that, you can go ahead and get the voltage. What you're going to end up finding out is that the voltage on the primary side over the voltage on the secondary side is equal to the number of turns on the primary side over the number of turns on the secondary side. And that is equation, you'll find it in your book. When you're looking at it, I thought I wrote it down already, but I didn't write the number. Oh, that's equation 29.5. Okay. Also, you can, using Ohm's law, you can also discover that I primary over I secondary is actually the opposite of this. So I'll get N secondary over N primary for this one. So here's one equation that's helpful. And this is called the transformer equation, by the way. That transformer equation says, let's say we have, from the power company, I've got, let's say 10,000 volts on the primary side, okay? And let's say I have 1,000 turns on the primary side. Now I want to send this voltage, to send the current actually out to some distant substation that's going to deliver it to a neighborhood, and I got to send a buttload of current. Well, it turns out that you can't really change the resistance of the wires. You're basically going to choose a metal, and then the distance from the power plant to the substation is fixed. So whatever that metal is and however large a gauge you use, that's going to dictate what your resistance is. So it's not much use to talk about the power as you know, IV. It's more important, because you don't know how much the voltage is going to drop across that. It's more important to do basically I squared. Remember, P equals IV, and then V equals IR. So it's P equals I squared R. So that's the actual power loss. So the larger the current that you have going through that power line, the more power you're losing just to heating up the wire. So what companies try to do, they have to send out 200 amps per house. If you're serving 1 million houses, say, then that's 200 million amps. 200 million amps squared means a buttload of power loss. But if they can instead jump this up from 10,000 volts to, say, 1 million volts, so we want the secondary to be 1 million volts, then the current, since the voltage jumped up by a factor of 100, the current will drop down by a factor of 100, and therefore the power loss will drop down by a factor of 10,000. So that's why they do those high voltage lines going to the fields. In order to make this happen, I might ask you, what is the number of turns in the secondary? So this is how we use the transformer equation. We say VP over VS is equal to NP over NS. And I say VP is 10,000. VS is 1 million. And NP is 1,000. So I solve for NS. And I think you can see that NS is going to be 1,000 times 1 million over 10,000. These three will cancel out with that. That guy will cancel out with that. So I got 100 times 1,000. That's 100,000 turns. So if this is 1,000, if this one's 1,000, I got to make this one to 100,000, and incoming voltage of 10,000 volts will be jumped up to 1,000,000 volts. And that, by this equation, will give us, instead of 200 million amps, it'll give us 100 less than that, because our factor was 100. So that's a typical use of the transformers. Now, in order for this to work, you actually have to have a AC power supply. Well, it turns out, thanks to our understanding now of Faraday's law, that whenever you have a coil of wire like that, and it's free to spin about some axis, when this coil of wire is free to spin about some axis in a magnetic field, say between the ends of a magnet, this would be the north end and this would be the south end, then the flux is going to become a maximum when the plane of the coil is perpendicular, or excuse me, is parallel to the front faces of the magnet. The flux is a maximum. But if you had this coil of wire connected to, say, a propeller, and that propeller was sitting inside of a boiling vat, then the smoke coming up from the boiling vat of water would actually cause this to rotate. As it rotates, it would actually generate a current according to Faraday's law, and that current could then be tapped using little brushes and rotor stats and ring clips and stuff like that. That current could be tapped and ran off as electricity in an AC manner. So it's automatically going to come up like this, because each time the current changes as a result of the changing flux, we're going to get the changing of the voltage. So that's how electric motors work. That's how power turbines and stuff like that work. So if you had a nuclear power plant, basically what you'd have is nuclear reactions heating up water. The water then turns to steam, drives a turbine that rotates a big coil of wire in between two strong magnets, and that creates a current that can then be shipped out. And of course, Tesla was the one that gave us the 60 hertz signal that we chose to use. But basically what that means is this goes through a full sine cycle every 60 times every second. So I hope that helps as far as the chapter 29 stuff goes. The chapter 30 stuff, we're pretty much out of time. This is enough to get you started on your test. I think I've done enough of the type of examples and explained it well enough where you can actually do the stuff that's on the test, as well as the examples in the book. So why don't we open it up for questions, and anybody that needs a split can, but if you have any questions, stay and ask them of me. So anybody have any questions?
What will we have to do to have our grade just be based on tests rather than homework?
You don't have to do anything. I automatically check that. So at the end of the semester, basically I compare. The difference is, remember, when I just do tests, I don't give you the boost of the lab grade, which is almost a free 100 for 20%. It's just averaging all the tests together with the percentages they're supposed to be, and comparing that to your syllabus grade, and the higher of the two is the one I give you. Because to me, you gotta sort of show that you can peak at the right time. So peaking on your tests, even if you didn't do enough homework the way that I assigned it, means that you still got the material. So I'm okay with you doing homework your own way, as long as you can perform on the tests. So that's the way I handle that. So yeah, I'll give you the grade, the higher of the two grades, no matter what. It makes it a little bit more time for me to calculate, but it's really not that big a deal. I put it in two separate spreadsheets and just run it. Anybody else have any questions?
Wait, so are you still dropping one test grade? I missed that part. I'm sorry.
Absolutely, yes. I'm still dropping one test grade.
Cool.
So that should help everybody. Anybody else? So here's what's going to happen as far as the final goes. If I have any more technical difficulties that prevents me from putting chapter 30 and 31 up, then the final exam will be on these same 3 chapters that this last test is on. If I can get 30 and 31 up, then the final exam will be just on those 2 chapters. If I can only get 30 up, it will only be on chapter 30. Okay, so it's not comprehensive, but like I said, I wanted you to make sure you're prepared. So if I screw up and don't get 30 up or 31 up, then your final exam is just going to be a test on the same material, including chapter 29. Does that make sense to everyone? All right, well, thanks for being understanding. Again, I apologize for not getting that stuff done. Email me if you have any problems. Your grades are sort of correct now in the grade book, other than I have not shown the drop test yet, because I don't want to show that until the very end, because when I let students know what their grade is going into the final perfectly with the drop test, they tend to do worse on the final. Like I can see them doing these calculations in their head. Well, I can get a 22 and still get my C, and then they end up scoring an 18 and they get a D or an F or something. So I don't like that. So I like to leave a little buffer in there so y'all get a little pleasant surprise at the end. I know that's not very treating y'all like adults necessarily, but I treat y'all sort of like y'all my kids, even though you're, you know, grown people. I mean that affectionately, not meanly. So anybody have any questions before you split? All right, everybody's free to go then. Have a good day and keep in touch. Let me know anything. Don't forget to send me emails regarding your practice test scores of 80 or higher. I want to know specifically exactly which practice test and how many times you score an 80 or higher, and that's going to add to your homework points. Have a good day, folks. Bye-bye.